Good morning, lads and ladies. Welcome back. Today, we're here. It's the last day. It's the final day of Calc 2. You guys have put in non-trivial amounts of work for the last 15, 16 weeks. And today is the last day you have to sit here at 9:30 in the morning on Zoom and watch my ugly ass spew mathematics at you. So, congratulations. And I hope you take some amount of delight in making it to this point. I do apologize for Wednesday. We were dealing with some shit at the household here that really could not be delayed or pushed back, and it was totally unexpected. Showed up out of the blue, and we just didn't have a choice. So life does that to us sometimes. I'll be adjusting the material we go over today and the plans for the test. Of course, you saw that announcement accordingly. So instead of doing the exam today, obviously we're going to be doing a take-home test, and that's fine. That's not an uncommon thing for me to do in Calc 2 classes anyway. But it means we only have the one day here to talk about integration in polar coordinates, and that's a little disappointing because it is pretty cool stuff. And I also wanted to kind of walk you through some more graphing problems. So that's what we're going to do today. We're going to do some more graphing problems, and I'm going to show you how to do integration in polar coordinates, which is actually a really nice thing. If you've been taking the time to go through the homework, then you may have noticed a theme to some of the problems. I'll pull up the problems I'm thinking about and kind of try to discuss that theme with you before we dig in. Okay. Let's do this. Oh, I need to turn on the, safeties need to turn on the screen share. Okay. Alrighty. So, actually, before we do this, let me do the title part. This is, as always, and for the last time, MAC2312 section 004, which is Calc 2, and the date is December 3rd, 2021. And today, we're talking about areas. And which is section 10.4. So 10.3 had some stuff about tangent lines in polar coordinates, and 10.4 also has some stuff on arc lengths and polar coordinates. Neither of those things are things that I am going to test you on or discuss, because the reason you do a coordinate transform, the reason you go from rectangular coordinates to polar coordinates, is because some problems become nicer in polar coordinates than they are in rectangular coordinates. The tangent line problem only gets worse, and the only way to solve it is to think about polar coordinates as parametric curves, which is not nice. Arc length, similarly, right, is not nice in polar coordinates. It doesn't get better, it gets worse, and there's no reason to do that. And in all my years in mathematics as a teacher and as a researcher, I've never seen any reason to work an arc length problem in polar coordinates. However, area problems, those can be very nice in polar coordinates. So here we go. These questions are designed to get at what I'm talking about now. Some curves are much nicer to discuss in polar coordinates than they are in Cartesian or rectangular coordinates. For example, a circle with radius 4 and center 1, 2, or a circle centered at the origin. So if I want to talk about a circle of a given radius, in Cartesian coordinates, we know this is x minus 1 squared plus y minus 2 squared equals 4 squared is 16, which is hideous, right? I mean, this is an implicit function or an implicit expression, not solved for x or y, and cannot be solved explicitly for x or y without using like plus and minus square roots. It's not pretty. It's not. Circle of the origin, radius 1, constant function 1 in polar coordinates, right? In Cartesian coordinates, this would be x squared plus y squared equals 1 squared. But in polar coordinates, right? So in polar coordinates, this would just be r equals 1. So I know which one I think of as a simpler expression. This, right, by miles over this. And you'll see similar sort of stuff on the other problems of this nature. So the main idea, and I did see that in the chat, I'll discuss that in just a second. Main idea some curves and regions are much simpler to describe in polar coordinates than rectangular coordinates. For example, the unit circle. All these black pens are. Yeah. The unit circle can be written as x squared plus y squared equals 1, or as r equals 1. Right, because r squared is x squared plus y squared. So one of these is a pretty nasty implicit expression that cannot be solved for x or for y without the use of like plus minus square root. The other one is a friggin' constant. If you needed to find the area inside the unit circle by setting up an integral, you would solve this for y. You get plus and minus the square root of 1 minus x squared. And then you'd have to integrate that from like 0 to 1, and then use symmetry, multiply by 4. It's not pleasant, right? It's a difficult integral. That integral requires trig sub, right? You wouldn't have even known how to do that back in the day. Now we do, right? Now you know trig sub in theory. But yeah, solving this for y and integrating to find the area is really rough. Integrating this is a piece of friggin' cake because it's a constant. So many problems. And I want to emphasize this for my physics and engineering people. Many problems that come from point-like sources of fields have radial symmetry, right? Like if I'm holding a point charge in my hand, if I've got a little charged particle here, that's going to create an electric field everywhere in space, right? From here out to the moon and past. And that field has radial symmetry. It's exactly the same over here as it is over here, as long as that distance from the point is the same. So anywhere in space, it's going to be the same, as long as you know, you just care about the distance. So if you had to do some sort of flux integral, I don't know if you guys know the term, like, or you're trying to figure out the change in electric potential, right? So you want to carry another charge in your pocket from the moon up to the charge I'm holding in my hand, figure out how much work you have to do based on the electrostatic forces. Any problem like that, where you have radial symmetry, is going to be much nicer if you set it up in polar coordinates and gravity stuff. Physics 1 folks, right? If I have a mass here and I want to know what the gravitational field looks like anywhere in space, or I want to calculate the work that's done to carry another mass, you know, from here out to somewhere else, all of that is so much nicer if you think of it in a coordinate system that itself has radial symmetry, like spherical or the 2D versions, polar coordinates. Okay. There was a question in chat about the study guide. So because test 3 is a take home, let me actually sneak this in as an announcement. So normally test 3 would get its own study guide, right? But because test 3 is a take home, it will not have a study guide. However, I can make a study guide for the final if you want. Is that something we would want? Just shout out, let me know.
Yes, Professor.
Yeah, okay. Instead, there will be a study guide for the final. Now, I want to be clear, the final exam is comprehensive, covers material from the whole semester. If I were to make a study guide that had like one problem of each type, that would be a, way too long study guide. So I can't do that, or I won't do that to you because that would be cruel. So instead, what I'm going to do is I'm going to kind of cherry pick a few problems from each chapter that I think are likely to be problems of the type you might have forgotten something about, or stuff that I think you maybe need a refresher on, or a little extra practice with, or stuff that I have a bias for and might put on the final. So the study guide isn't meant to be the study guide isn't meant to be representative of everything that could be on the final, but it will have the problems that I think are most significant. All right, let me see, the chat's got a handful of questions here. So release the exam, review it. Yeah, if you look on the written work, you should be able to see all the feedback there. So I don't release a key. Instead, when I go through and grade your stuff, if you made a mistake, I correct the mistake, show you what went wrong and how to fix it. If you haven't been reviewing that, please do. Take home test after class, and then Friday's class. Open. So there are two more like test grades this semester, right? There's exam 3, which I'm going to be given as a take home. And what that means is I'm going to publish a PDF on Canvas, which you will save, print, fill out, right? Solve the test, right? And then scan it and submit it. Like a worksheet, right? Basically the same rules as the Jello worksheet. The final exam is a regular proctored exam, right? The final exam will be in Canvas, all the same like rules that we had for the rest of our exams. And it's not an all-day thing. No, the way it works here at Santa Fe, you have to take the final at the prescribed time, and we have to do the final in person. I think we touched on this the other day, but the final exam is going to be for your class on the 8th at 8 a.m. And you cannot take it at the testing center. It's not an all day whenever you want thing. It's got to be on the 8th, which is next Wednesday, and it's got to be at 8 a.m.
And Professor, like take home, is it going to be like the exam we could take it all over the weekend, or we have to take it today before 12?
The take home test I will publish for you today, and you can work on it up till the day of the final. So the take home is going to be due at the start of the final exam. So you can work on it today, tomorrow, all the way up through the 8th if you want.
Oh, okay, perfect.
Yeah, Kylie, if you took your test at the testing center, so then I graded them on paper. And what that means is that if you want to look at the feedback, let me know. Send me an email or come by an office hour. What most people have been doing is coming by an office hour, and then I put the test up on the document camera and we review it together. But if you would prefer, I could just scan it and send it to you. But yeah, if you took the test in person at the testing center, the feedback is on physical paper, and we would need to communicate somehow to get that to you. Okay. So let's get back to what we're talking about. Some graphs are much nicer to describe in polar coordinates than they are in Cartesian coordinates. And this is just one example, but there are more extreme examples. Let's take a look at some of these because we haven't done a whole lot of graphing yet. Okay, let's sketch the graph, polar coordinates, right? R equals 2 cosine of 3 theta. The trick to doing this, the trick to graphing a function in polar coordinates, if it's not super simple, like we graphed R equals a constant the other day, we graphed theta equals a constant the other day. What you're going to want to do here is sketch it in rectangular coordinates and then transfer that graph over into polar coordinates. Still stuff in the chat about the take-home test. Test 3, no honor lock. Nope, it's not proctored. It's not an online test. So you just print the test, solve the problems, scan it, and submit it. There's going to be an honor pledge on the test, and maybe since folks are asking, I should reiterate this, turn on the camera for angry face. We've said this, but just to be clear, I have Mathway, Photomath, Symbolab, all that shit on my phone too. I know what a real solution looks like, and I know what a copied down from Mathway, whatever solution looks like. So yeah, take home test, you're gonna do it at home. Nobody's gonna be watching you. You're gonna sign a little thing at the top that says, I swear I did not get any help from anybody. And if you do, I'll be able to tell. Not only do I know what a real solution looks like compared to a bullshit copied from Mathway, Symbolab, whatever solution, I also know you guys at this point, right? I have lots of samples of your work, so I know what your workflow looks like. So no honor lock, nobody's going to be watching you. It's you're just going to solve the problems on your own, then scan the thing and submit it, and I will grade it. But yeah, don't use outside resources, none of them, right? No other people, no YouTube videos, no apps on your phone, no tutors, none of that. The things you are allowed to use are the textbook and your notes, right? So you've got access to those massive resources. You've got several days to take the test. It's not any longer or harder than a regular test. So we can all do very well on this, but please don't cheat, right? I will notice. And I failed at something like 8 people over the summer. I know, over the summer, 4 people on a take-home test for cheating. Caught them. So please don't do that. All right. How do we graph this? I want to graph this in polar coordinates. The trick is to first graph it in rectangular coordinates. And rectangular coordinates is like the normal thing, right? Where you've got your vertical axis and your horizontal axis. And you always want to make sure your graph goes out at least to 2 pi. Because when we go to transfer this graph into polar coordinates, in order to kind of spin all the way around that polar system once, theta needs to go out to 2 pi. So in rectangular coordinates, this is your r axis, and this is your theta axis. And you're graphing a regular cosine wave. This is something everybody learned how to do way back in trigonometry, right? This is a regular cosine wave. Its amplitude is 2, and its period is 2 pi over 3. All right, everybody remembers how you find the period for a sine or cosine function. You just take 2 pi and divide it by this number. So here's 2 pi, here's pi over 2, 3 pi over 2. I'm not going to mark them, but I am going to mark 2 pi over 3, right? So 2 pi over 3 is a little bit south of pi. So this is a cosine wave with amplitude 2 that completes a full cycle by the time you get to 2 pi over 3. So it's going to start up here, and it come all the way down, all the way back up by the time you get to 2 pi over 3. And then halfway in between these is going to be 1 pi over 3. So this wave is going to look like this. There's one full period. And if we want to go out through the next period, if you add 2 pi over 3 to 2 pi over 3, you get 4 pi over 3. And 4 pi over 3, if you think about your unit circle, 1, 2, 3, 4, it's going to be right about over here. So we need to come all the way back down and then all the way back up by the time we get to 4 pi over 3. And then if I add another 2 pi over 3 to this, I'll get 6 pi over 3, which is 2 pi. So we've got one more full cycle that we're gonna run through. And so halfway-ish back here, and then all the way back up here. Okay. So there is this curve graphed from 0 to 2 pi. I've already got these mins and maxes labeled, right? This is pi, this is at 0, this is at pi over 3, this is at 2 pi over 3. This one we should label here. Where is this? Halfway between 2 pi over 3 and 4 pi over 3. So think about your circle, the unit circle. Pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3, 5 pi over 3, 6 pi over 3. This is pi over 6, right? This first root here. 2 pi over 6, 3 pi over 6, pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5. 5 pi over 6, 6 pi over 6. This would be here. So the trick is to count in multiples of pi over 6, right? You know, each one of these little gaps is pi over 6. So 1 pi over 6, 2 pi over 6 is pi over 3. The next one would be 3 pi over 6, which is pi over 2. 4 pi over 6, which is 2 pi over 3. 5 pi over 6. 6 pi over 6, which is pi. 7 pi over 6. 8 pi over 6, which is 4 pi over 3. So it'd be 9 pi over 6, which is divide top and bottom by 3. 3 pi over 2. 10 pi over 6. 10 pi over 6. And then 12 pi over 6 is 2 pi. So here's your graph in rectangular coordinates. And what we want to do is transfer this into polar coordinates. If you don't remember how to graph sine and cosine waves, then you want to look at your notes from trig or get a little refresher somewhere. It's not that hard. You find the period, you find the amplitude. If you're unlucky, you have to find a little horizontal shift. It's really not that bad. The game from here is to now sketch this thing in polar coordinates. Now transfer graph polar coordinates. I think it's pretty clear that the multiples of pi over 3 are important to this problem, right? This graph, because he's got mins and maxes at those. Also, the multiples of pi over 6 are important. So I'm gonna mark out here all of the multiples of pi over 6, and that will include the multiples of pi over 3, of course. Okay. So this ray, this is pi over 6. This ray is pi over 3. Of course, that's pi. This ray is 2 pi over 3. This ray is 5 pi over 6. This ray is 7 pi over 6. This ray is 4 pi over 3. This one down here is 5 pi over 3. And this one here is 11 pi over 6. And what I want you to imagine, pay attention here, is a little arm spinning around. And as it spins, there's a little dude running in and out on the arm. Let me mark this as 1 and 2 along my polar axis. So this curve in rectangular coordinates is going to be translated into a curve in polar coordinates by following the rule that the dude, this is your little radius arm, his distance from the origin is the thing that's dictated by the r values here. So when theta is 0, he's out here at distance 2. And as theta rotates up from 0 towards pi over 6, he's running inward because this graph is decreasing. And by the time I get to pi over 6, my little dude has run all the way back into the origin. This is going to trace a curve. I'm going to trace a curve that looks like this. All right, my little dude starts out at the end, and as I rotate up, he's running in. And by the time I am tangent to pi over 6 here, he has arrived at the origin. As my arm rotates past pi over 6 towards the next important one here, which is pi over 3, my radius has become negative. It's poking back out from 0, but it's become negative. And that means instead of drawing in this region over here, which is normally where I am between pi over 6 and pi over 3, I'll be drawing in the mirrored region over here. Because remember, when your radius is negative in polar coordinates, you reflect through the origin. And by the time I get to pi over 3, which would normally be right along here, my radius will have come out to a max of 2. So if you like, the point where r is 2 and theta is pi over 3, normally that would be right here. But because r is negative 2, we will be reflected through the origin here. And instead of drawing in here as we rotate through that region, we will be drawing out here. So this little portion of the curve here, our theta is rotating from pi over 6 to pi over 3. Stop getting my hand in the way. There we go. Theta rotates from pi over 6 to pi over 3. Normally, I would be drawing over here where the tip of the pencil is. But because r is negative, I will be drawing over there. And that radius is going from 0 out to 2. It's just negative. So this would be the polar point, -2, comma, pi over 3. Let me make that nice and clear. -2, comma, pi over 3. That is this polar point. And my arm continues to rotate around. As we rotate past pi over 3, we're here right now. As we rotate past this towards pi over 2, my radius, which was out at a max here, is coming back in, which means this point is going to be coming back into the origin. Imagine this rotating. As we first start to rotate, we're out here at 2, We run into the origin. You see that coming in when we're at pi over 6. And then as we rotate past pi over 6 towards pi over 3, we're drawing over here because r is negative. As we rotate past pi over 3 towards pi over 2, r is still negative, but it's retreating back to the origin. So we will get a shape like this. So now we're here, we're at pi over 2. And r is once again going to become positive. So as I rotate past pi over 2 towards 2 pi over 3, I'll be drawing in this region. What's my radius doing? It's coming from 0 and it's growing back out to 2, and it reaches that max of 2 at 2 pi over 3. So this is going to create a piece that looks something like this. And this would be the polar point positive 2, comma, 2 pi over 3. So we are now here. As I rotate past 2 pi over 3 towards 5 pi over 6, we're now talking about this part of the graph. My radius was at a max of 2 here, and as we rotate past 2 pi over 3 towards 5 pi over 6, my radius is coming back in. So we're going to start coming back in, and we'll come in tangent and arrive tangent to 5 pi over 6 at the origin. Something like this. And you can sort of start to get a feel for what's going on with this graph. As we rotate past 5 pi over 6, which is right here towards pi, r is once again negative. So instead of drawing in this region from 5 pi over 6 to pi, I'll be drawing in the reflected region over here. My radius is going to poke out from the origin. Would be tangent to this line, but because r is negative, we're reflected over here. And when we reach this max of -2 at pi, normally here is the point 2 comma pi. The reflected point is over here. This is -2 comma pi. And you can ask yourself what's going to happen as we continue through the rest of this curve. If I keep rotating, so really I should put the pointy end over here so you can see. Right now we are at the polar point -2 comma pi. So here's 2 comma pi, it's reflected over here. And as I keep rotating, we follow what's going on here. My radius should start retreating in. By the time I get to 7 pi over 6, it will have come back to the origin. It's negative, so instead of drawing in this region, we're drawing over here. That's just going to trace this portion again. So as we run through this part, we are tracing, as we run through this part, we are tracing this portion again. As we run through this part, r is now positive, so past 7 pi over 6 towards 4 pi over 3, we're going to poke out. We're going to arrive at a max of 2. So the polar point 2 comma, this is the same as 2 comma 4 pi over 3. We get there again. So we're going to trace this whole curve twice as theta goes from 0 to 2 pi. This curve is called a petal graph with 3 petals or loops. And it is traced twice as theta goes from 0 to 2 pi. Now, this procedure of going from the rectangular graph to the polar graph is one that you need to practice. It doesn't come naturally to anybody at first. It always feels quite challenging. And for years, I've been hunting for really good visual aids for this. I haven't found much that's very good. So if you find anything cool, let me know. Like a YouTube video that animates that procedure very well, I think would be super helpful. I want to try one more like this. and then we're going to talk about finding areas. The procedure is always the same. You graph the thing in rectangular coordinates and then transfer that graph over into polar coordinates by thinking about the rotating arm. Let's do a limit sign, maybe something like negative every now and then. Let me grab an example that is nice and tractable and grab one from your book. Yeah, something like, that would be fun. Yeah, sure. 1 plus sign. You can imagine that the pedal graph we just drew, his Cartesian equation would be a nightmare. It's a terrible, terribly ugly thing. But in polar coordinates, it's quite simple. The same is true of this guy. So if I want to sketch 1 plus sine theta, I know that's a sine wave with period 2 pi, amplitude 1, and it's been shifted up by 1 unit. So I like to draw the kind of equilibrium line here. The amplitude is 1, the period is 2 pi. We haven't modified this, but there's a vertical shift up 1 unit. So this is the regular sine wave, just bumped up 1 unit. I'll mark off a full period, a half period, a quarter period, and a 3/4 period. You know that sine starts in the middle of his amplitude, increases to our max at the quarter period, comes back through here, min at the 3/4 period, then max again here. So this wave looks like this. Again, this for theta axis, this for r axis. And then I want to transfer this into the polar coordinates. Just like I did on the previous problem, anywhere there is like an equilibrium, a max, or a min, I want to draw rays along that in the polar system. So I have kind of like a grid, a polar grid. So that's 0, pi over 2 pi, 3 pi over 2. Those are all nice things here already. If I mark this as 1, my little arm, starting when theta is 0, the guy is out here at 1. So the first point on this polar graph that I will draw is the polar point 1, 0. As theta rotates up from 1 towards pi over 2, r is growing out to a max of 2. So as this rotates, my little dude is running out. He's going to reach a max of 2. So that's going to look something growing, something like this. And this would be the polar coordinate point 2, pi over 2. As my little arm rotates past pi over 2 through the second quadrant towards pi, r is coming back in. So my little dude is walking back in as I do this. And by the time we get to pi, he's back at 1. So that will give me something like this. This is the polar point 1 pi. Kind of try to visualize the little guy running out along the arm as I rotate here. See, he's running out more and more and more. R is increasing, 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 until I get to that max R equals 2. When this thing is up here at pi over 2. And now as I rotate past pi over 2, my little guy is running in, he's running in, he's running in, he's running in. You see that radius getting smaller and smaller and smaller until I get to pi, where he's at 1. Out here at distance 1 along this radial arm. As I rotate past pi, he's going to continue running in, and he's going to make it to 0 by the time I get to 3 pi over 2. So that means this is going to tuck in and come into 0 tangent at the 3 pi over 2 line. And then as I rotate past 3 pi over 2, back around towards 2 pi, my little dude is going to run back out, but only going to get to 1, right? Because that's this point, it's 1 comma 2 pi. So we're going to come back out and join up with this. Now, I was joking with my wife when she took this class. These curves are called cardioids. Because it's like cardioid, not teoid, cardioid, like cardiac, like a heart, right? It's kind of a heart-shaped curve. I've also, my wife and I were talking about this, called them bootyoids, because, you know, kind of looks like a booty. Up to you, right? Up to you. But if you call it a bootyoid, people are going to be really confused. So stick with cardioid when you're talking math, folks. All right. We'll do some more examples like this, but before I do any more graphing examples, I want to talk a little bit about how to find areas. So imagine that I wanted to find, say, this area. It would be nice if you just had to integrate this function. But if you integrate that function from 3 pi over 2 to 2 pi, you're going to get this area here. And the first myth I want to dispel, because I've heard this said by people recently, not in your class, mind you, but talking to students, other students taking Calc 2 with different faculty. These areas, we definitely know how to find this area. This area is the integral from 3 pi over 2 to 2 pi of 1 plus sine theta d theta. These areas are not equal. These areas are not the same. The process of transforming the graph from Cartesian coordinates to polar coordinates is not area preserving. There's a name for such maps, but I don't need to tell you what that name is because this isn't one of them. But it's not anything like an isometric map. Right? So if you want to find this area, you can't just say, okay, I'm going to find this area. I'm just going to integrate the function. That doesn't work. There is something else which does work, and I want to kind of explain to you where it comes from. The first thing I want to say again, area here, not the same as the area here. And similarly, and this is the context I heard it before, the area of a loop of a pedal graph is not the same as the area of one of the things here. Okay. So if that doesn't work, what does work? I'm going to imagine setting up a Riemann sum. So imagine I have a curve here, r equals some function of theta. And I want to find the area between two angles, say this origins down here. I want to find the area between here, which I'll call alpha, and this angle, which I'll call beta. The way you do this, or at least the way you conceptualize it to build the Riemann sum, is to imagine chopping this up into a bunch of little regions, right? And kind of instead of rectangles, you have these little Riemann segments, which we approximate as though the function is constant there. So I would approximate this like this, like this. Remember what a constant function is in polar coordinates. It's a circle. So to build the Riemann sum, for the area enclosed by a polar curve R equals R of theta from theta equals alpha to theta equals beta. We're doing the same thing that you do in rectangular coordinates. We partition the theta interval alpha to beta into n equal subintervals. Call them length delta theta. I don't want to call it a length because it's really a rotation. So I'm just going to say delta theta. All right, so each one of these little angles in here is delta theta. Then, in each region, we approximate R of theta as a constant function. So alpha you could call theta 0, and then this first angle here you would call theta 1, theta 2, theta 3. Constant function R of theta I, right? This is like your height. So the polar point here would be R of alpha, comma alpha. The polar point here is R of theta 1, comma theta 1. The polar point here is R of theta 2, comma theta 2. This is R of theta 3, comma theta 3. And this would be R of beta, comma beta. And beta would be like theta 4 here, and alpha would be like theta 0. The area enclosed by one of these, call it Riemann chunk, I don't know. I don't want to give it away. Say the area enclosed by this little blue, vaguely triangular looking shape is 1/2 R of theta I squared times delta theta. Because each Riemann chunk is a sector of a circle. Right, so again, a constant function in polar coordinates is a circle centered at the origin. So when I'm saying from here to here, I'm going to approximate my function as being constant, right? Just like saying the height of the rectangle is constant in the regular rectangular setting. I'm going to say here the radius is constant from here to here, and I'll approximate that as r of theta 1. Well, then this shape that creates, it's not a triangle, it's a sector of a circle. And if you remember how to find the area of a sector of a circle from your geometry classes, if this angle here is theta, and this is a sector with radius r, then this area in here you know it should be pi r squared when theta is 2 pi. If you go all the way around the circle, that should give you pi r squared. You also know it should be a linear function of theta. If you cut the angle in half, the area should go down by half. So it's a linear function of theta that gives pi r squared when theta is 2 pi. There's only one of those, and that's 1/2 r squared theta. So each one of these little sectors here has area 1/2 times the radius squared times the little angle inside, which is delta theta. And now we're ready to write down the Riemann sum. I know each little area is this. So the Riemann sum for the area bounded is approximately sigma I from 1 to n 1/2 r of theta I squared times delta theta. Right, this is the theta is not being squared, it's r of theta squared. I guess I should put parentheses here. And as n goes to infinity, this Riemann sum becomes an integral, the area becomes exact, blah, blah, blah. Write it out. And as n goes to infinity, this becomes, right, the shaky equal sign becomes an actual equal sign, and the sum becomes the integral from alpha to beta of 1/2 r of theta, my function, squared d theta. And this is the thing we need to remember. Really, from this section, there's only two things you need to know. You need to be comfortable graphing curves in polar coordinates, and I truly believe that's the harder part. The other thing you need to know is this formula for finding areas. So let's return to our bootioid. Now that we have this formula in hand, our cardioid, and see if we can find this area. You ready? Everybody's got this integral formula down? If you want to, we can also calculate this just to verify that they're different. I said that earlier. the area enclosed by the polar graph is integral 1/2 my function r of theta here. Remember, r was 1 plus sine theta. So this is 1 plus sine theta, but it goes into that formula. It's 1/2 r squared d theta. And we need to integrate from the angle here to the angle here. Well, what was this point? What were the polar coordinates of this point? Where did he come from up here? Specifically, what was the theta value? We know the radius is 0. Remember the arms spinning around, spinning, 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 still spinning, still spinning. You guys too young for this meme, but they just keep spinning all the way around to here. This is when he retreated into the origin. Yeah, 3 pi over 2. So alpha, we're going to integrate from 3 pi over 2, and then we kept spinning, spinning, spinning. We arrived here at 2 pi. So that is the integral which will give me this area. The 1/2 can pop out. That's integral 3 pi over 2 to 2 pi. We need to FOIL this. That's 1 plus 2 sine theta plus sine squared theta. So the other skill that you need here, right? You need to remember how to graph and the area formula. The other skill you need here is trig integrals, right? Obviously, we're going to be doing integrals that involve trig functions. These first two pieces are easy. How do you integrate sine squared? Does anybody remember the tool we need for this? Yeah, very good, Richard. We use the half angle identity. I'm glad somebody remembers that. That makes me smile. The half angle for sine is sine squared theta equals 1/2 times parentheses 1 minus cos 2 theta. While we're here, the one for cosine is cos squared theta equals 1/2 1 plus cos 2 theta. Now, obviously, I just need the first one here. So this is 1/2 integral 3 pi over 2 to 2 pi 1 plus 2 sine theta. I'll go ahead and distribute the 1/2. That's plus 1/2 minus 1/2 cosine 2 theta d theta. And there are some like terms I can combine. I've got a 1 here, that's a constant, and a plus 1/2 here, that's a constant. Those can combine to a 3/2. So I've got 1/2 integral from 3 pi over 2 to 2 pi of 1 plus 1/2 is 3/2 plus 2 sine theta minus 1/2 cosine 2 theta d theta. And now each of these antiderivatives is very straightforward. 3/2, that's 3/2 theta. 2 sine theta is going to be -2 cos theta. And 1/2 cos 2 theta, the cos 2 theta part would integrate to sine 2 theta over 2. So this is minus 1/4 sine of 2 theta. And we evaluate from 3 pi over 2 up to 2 pi. I was looking back through exam one stuff the other day, and some of the integration was really rough. So if I had to make one recommendation for the final, especially if your exam one was rough, is make sure that you've put an appropriate amount of time into solving integrals. Section 7.5 is a really good place to practice this because 7.5 has a mixture of all the integration problems from the whole book. I will put some in the study guide, but I suspect that many of us need lots of practice on that. So please make sure you spend some time working on integrals before the final. Now, if I plug in my bounds, I'll continue over here. At the upper bound, 2 pi, I'll have 3 over 2 times 2 pi, which is just 3 pi. Minus 2 times the cosine of 2 pi. The cosine of 2 pi is 1. Minus 1/4 times the sine of 4 pi, which is 0. I'll write it as minus 1/4 times 0, just so we can kind of see where pieces are coming from. And then I need to subtract off what we get at 3 pi over 2. When I plug 3 pi over 2 in here, that's 9 pi over 4. Minus 2 times the cosine of 3 pi over 2. Well, the cosine of 3 pi over 2 is 0, so this is all right, minus 2 times 0. Minus 1/4 times the sine of 2 times 3 pi over 2. Well, that's the sine of 3 pi, which is also 0. Okay, so what do I get? I've got 1/2 3 pi minus 2 minus 9 pi over 4. You could put the multiples of pi together if you want. 3 pi is the same as 12 pi over 4. 12 pi over 4 minus 9 pi over 4 is 3 pi over 4. And this is good. I would leave it like this. You can distribute the 1/2 if you want. You could have a further common denominator here, but because it was pi, it's not going to be pretty either way. So that's it. That is the area enclosed there. Let's look at our petal graph. Maybe just for fun, let's graph one more petal graph. Let's do something fresh. That last one, what did I do? Was it cosine of 3 theta? Yeah. So to cook up our final area problem here, let's sketch R equals about 3 sine of 2 theta in polar coordinates, and find the total area enclosed. The amplitude is 3. The period is 2 pi over 2, which is pi. And there are no shifts. So the rectangular graph here, where the vertical axis is r and the horizontal axis is theta. Period is pi, it's a sine wave. We're going to start here. We're going to come through a full cycle by the time we get to pi. So let me mark off quarter periods as well. oh, sorry, the amplitude here is 3. Yeah, not 1. Let's change this to 3s. So it's going to look like this. From 0 to pi, there's 1 full cycle. And then we need to go through another full cycle as we go from 0 to 2 pi. I'm going to do this. Modulo my bad art, that's the game. These guys, the maxes and mins, those are at multiples of pi over 4, right? It's halfway between 0 and pi over 2. That's got to be pi over 4. Halfway between pi over 2 and pi, that's got to be 3 pi over 4. Halfway between pi and 3 pi over 2, that's got to be 5 pi over 4. And halfway between 3 pi over 2 and 2 pi, it's got to be 7 pi over 4. So if I want to transfer this into polar coordinates, I should mark off the multiples of pi over 4. All right, and I'll call this 1, 2, 3, just to give us a scale here. When I have done no rotation at all, my little arm is right here. The little dude is at the origin, right? Because we're starting here with theta is 0, r is also 0, so my dude starts here. As I rotate up from theta equals 0 towards theta equals pi over 4, my little dude is going to run out to a max radius of 3. So it's going to go like, and that's going to look like this. So this would be the polar point 3 comma pi over 4. It's the polar point we get by transforming that guy. As I rotate past pi over 4 to pi over 2, my radius is coming back in. So I'll come back in and arrive at the origin here, tangent to that ray. This is where things get complicated. When the radius gets negative, as I rotate through here, normally between pi over 2 and 3 pi over 4, I'd be drawing up here in the second quadrant. But because the radius is negative there, I will be drawing down here in the mirrored quadrant. We will come out to a maximal radius of -3. And so here would be the polar point +3 comma 3 pi over 4. Instead, we're going to be over here at -3 comma 3 pi over 4. And the curve traced on the way there is going to look like this. And something I like to do is to highlight which portion of the graph here comes from which portion of the graph here. So I'm going to do that for this because I think it's one of the more challenging things to see. This portion of the graph comes from this portion of the graph. Maybe I'll make it extra big up here because it's kind of hard to see. That portion gives this portion. And it's not entirely obvious because normally you'd think from pi over 2 to 3 pi over 4, you're drawing up here. But you're not, you're drawing down here in the reflected region because the radius is negative. All right. As this retreats back in, as we rotate from 3 pi over 4 to pi, my radius is still negative, but he's coming home to the origin. He's going to arrive tangent like this. As we rotate past pi, just a little bit past pi, my radius should start poking out a little bit. And indeed he does. And we're going to come out to a max of 3 when we get to 3 pi over 4. So this is the polar point, comma, 3, comma, 3 pi over 4. And as we go past 3 pi over 4, my radius starts coming in. He's going to arrive back at the origin when we rotate to 3 pi over 2. And as we rotate past 3 pi over 2 to 2 pi, normally we would be drawing over here. But because this radius is negative again, we're going to be drawing the reflected region, which is over here. And we will reach that max here. So it's going to be the polar point negative 3, comma, 7 pi over 4. And then we'll come back in as we get to 2 pi. All right. So this is another petal graph. This one has 4 petals. If you just have like a sine bx, r equals a sine bx, or a cos bx, those will always be petal graphs. The orientation of the petals and the number of petals are determined by the specifics. So the number of petals comes from this guy. If this guy is an even number, you will have double that number of petals. If this is an odd number, you will have exactly that number of petals, and it'll be traced twice as theta goes from 0 to 2 pi. Oh, did I goof up? Let's see. Should the third petal be 5 pi over 4? Maybe 3 comma. Yeah, I think so. Yeah, 3 pi over 4 had us over here. Sorry, this is 5 pi over 4. Thank you. Because we were positive there. He should be where he appears to be. Thank you, thank you. Okay, I want to find the total area here. And while it might not be obvious from my picture, because my picture isn't perfect, each one of these petals encloses the same area. There is a lot of symmetry here. So note, by symmetry, the total area is 4 times the area of one petal. And if I want to set up an integral for the area of one petal, I might as well do the first one here from 0 to pi over 2. Note though, if I specifically asked you to set up an integral for this petal, you would not be integrating from 3 pi over 2 to 2 pi as it appears, because this petal came from the theta interval pi over 2 to pi. So if I told you specifically to set up an integral for this petal, your theta values would be from pi over 2 to pi. And that's a little misleading. That's what I meant when I said, no, it's good to shade this for a second and remind ourselves what theta values it's coming from. But that's all. So the area I want here is 4 times the area of one petal. Which is 4 times the integral from 0 to pi over 2 of 1/2 my function, which is 3 sine 2 theta squared d theta. I can pop out the 1/2. There's also going to be a 9 from this 3 squared. So 4 times 1/2 is 2 times 9 is 18. Integral 0 to pi over 2 sine squared of 2 theta. 2 theta is what's left here. And now the integral of sine squared, we know how to do this. That's going to be 1/2, so I'll pop out the 1/2. That's 18 halves. Integral 0 to pi over 2. 1 minus cosine of 2 times 2 theta is 4 theta. 18 halves, that's back to 9 now. And then an antiderivative 1 will integrate to theta, and cos 4 theta will integrate to 1/4 sine 4 theta. And we evaluate this from 0 to pi over 2. When you plug in 0 here, you get 0. When you plug in 0 here, you get 0. So the only contribution comes from the upper bound. When you plug in pi over 2, this will be pi over 2. This will be 1/4 times the sine of 4 times pi over 2 is 2 pi. That's 0 again. So evaluating here, the only contribution is from the theta, and only at the upper bound, you get 9 times pi over 2. Or 9 pi over 2. And that's it. So, graphing in polar coordinates. It's fun stuff. I want to invite you guys to play around in that Desmos environment that I sent out last time. There are a lot of polar graphs that we don't have time to look at here together. Points, did I do polar graphs? Oh no, you don't need a special thing for polar graphs. So the polar points, if you're just getting used to this stuff for the first time, definitely play with this. You can move the point around by changing its amplitude, and you can plug in the angle you want here, right? But if we want to graph functions in polar coordinates, you don't need to do anything special. Oh, there's no new graph. New blank. You can just put in r equals 3 sine 2 theta. I do recommend changing this to the polar grid. That'll help you see what's going on. There are some other fun things like 2 plus this. Wow! Or 1 minus this. Or 1 minus that. Or 2 minus that. Or 2 plus all sorts of weird things, right? So I invite you to play with these. The cardioids, like 1 plus cos theta, or 1 plus sine theta, follow nice predictable patterns in the same way that the petal graphs do. All right, so like I said, if the angular velocity, the number in here, is an odd number, you'll have that number of petals and it'll be traced twice. If it's an even number, you'll have double that number of petals and it will be traced once. If you have a sine, they will be oriented like this, kind of starting in the origin. If you have a cosine, it will be out of phase by 90 degrees, or starting over here at the along the polar axis. But the rules for the number of petals are the same. All right, that's what I have for you guys today, and that is the end of Calc 2. So the very last things that I require from you are the ability to sketch graphs in polar coordinates and find areas in polar coordinates. Thankfully, finding areas is not hard, but the one thing I want to strongly emphasize, force you to remember, is that the area enclosed, say, by this little bit of the graph here, is not the area enclosed by one of these petals. Those areas are not the same. The transformation that takes this graph in rectangular coordinates and turns it into this graph in polar coordinates is not area preserving. So in order to find the area of a enclosed by a polar curve, you do need to use this different formula. All right.
Professor?
Thank you guys so much for hanging in through the semester. I know it's been tough. Questions in the chat. Study guide for test 3. Test 3 is a take home. There's no study guide, but I'm going to make a study guide for the final. That will be your third study guide grade. For the final exam, can you take it at the testing center? No. The final exam needs to be taken online with me. The testing center is very busy doing finals for fully online classes. So they are not going to allow us to do walk-ins for the final exam. Also, final exams have to be taken at the specified time. So we cannot do the like come in whenever you want thing. So the final exam, you're going to follow the Zoom link that I post on that day. You're going to join that Zoom link from your phone. You will set up your phone where I can see your desk, your hands, your paper. You will sign into Honor Lock on your computer, just as though you'd taken any of the midterms online with me. Do we drop the lowest test grade? No, we do not drop any test grades. However, the final exam will replace your lowest test score. So say you got a 50 on exam 1. It was bad, you weren't ready, you didn't know how hard this class was going to be. But then you get a 70 on the final. I will go back and manually replace exam 1, that 50, by a 70 after I grade your final. So those few questions. Study guide for test 3? No, but there is a third study guide. It will be the study guide for the final, and I'll post that later today. The final exam has to be taken online with me, cannot be taken at the testing center, and it has to be taken at the time in the syllabus, which is December 8th at 8 a.m. Put this shit in your phone right now. Not dropping any test scores, but we do replace the lowest midterm by the final, but only if it helps. Third exam is going to be due on the day of the final. So at the start of the final, you can work on that take-home test, exam 3, up until the very moment the final exam begins. But at that moment the final exam begins, you need to have submitted your take-home. So I strongly recommend finishing the take-home quickly. That way you can spend a little bit more time studying for the final. You can submit exam 3 whenever you want. You don't have to wait until the day of the final, but I will not take it after the day of the final. I will have office hours today. Yep, normal office hours. The final exam is written by me. So the last class here at Santa Fe that does a department final is MAC2312.005. Everything beyond that, exams are written by the professor, including the final. The format for the final will be the same as the format for the midterms. It's going to be in Canvas. There will be a few more questions, probably around 20 questions instead of 14. It will lean a little bit more heavily towards true, false, and multiple choice. And you will have 2 hours to take it unless you have some sort of accommodations. Okay. And
You said it's more multiple choice?
yeah, so in, like normally we have what, 4 true, false, 4 multiple choice, and 6 free response, something like that. This will probably be closer to like 6 true, false, 6 multiple choice, and then 8 free response. So it'll be about 20 questions. I haven't written it yet, but it'll be about 20 questions, and there will be a little bit more of it will be true, false, or multiple choice to speed up the grading procedure. Okay, any other questions you guys would like to ask before we wrap up our last meeting here? Okay, then thank you guys so much for the diligence you've put in over the semester. What was the last integral there? Here. If you're in a rush, I would just write this down or take a screen cap and then crunch it out. It's not too hard. 4, because 4 petals, and then the integral for 1 petal is 0 to pi over 2, 1/2 times our function all squared. And the answer came out to 9 pi over 2. That's including the 4. All right, I got to get running, guys. I hope you have a lovely rest of your day. If you need anything from me, need to talk, you're worried, you just want practice with problems, anything like that, reach out to me. You know the channels at this point. That's it. I'll see you guys for the final. Take care.
Thank you.
Of course.